Chapter 8 is right triangles, and we're going to begin with a pre-chapter 8 radical review. Now, remember radicals were like square root and cube root, and we studied those in the Algebra 1 text on page 15 and 16, and then again on page 246 to 250 something. Then we're going to look at similarity in right triangles. Within right triangles, there's some similarity concepts that brings up a lot of little rules. We're going to look at the Pythagorean theorem, a squared plus b squared equals c squared. You're familiar with that from 8th grade. You're familiar with that from Algebra 1 on page 177. The converse of the Pythagorean theorem we're going to use to determine whether a triangle is acute, right, or obtuse. Special right triangles, these are 30, 60, 90, and 45, 45, 90 triangles. These are also in the Algebra 1 text in chapter 9 of the Algebra 1 text. But some years I get to that, some years I don't. So this may or may not be a new concept, depending on how far you got in the Algebra 1 book. Trigonometric ratios, something that's generally introduced in geometry, sine, cosine, and tangent. It's finding missing parts of right triangles. That's what this whole chapter is about, finding missing pieces and parts of right triangles. And then we're going to use some trigonometric ratios for non-right triangles that really don't have a place in geometry. That's really getting into pure trigonometry. But we're going to go ahead and introduce that to you here. Then we have the odd answer solutions and the study guide. So here we go into the pre-chapter 8 review. Now, what we're going to be doing here is simplifying radicals. And I'm going to give you fancy definitions and I'm going to give you drills. In the Algebra 1 text on page 15 and 16, we simplified radicals, just breaking down a radical, I call it. We had already learned how to add and subtract them on page 1 and page 5, page 1, multiply them and divide them on page 5. And then in chapter 9 of the Algebra 1 text on page 246, we added radicals. Page 247, we multiplied radicals. On page 248 to 251, we learned how to simplify radicals, and that page 248 to 251 looks almost just like this, okay? Except I've got a few extra things in the geometry book. So on page 15 of the Algebra 1 text, we learned square root means what times itself equal. What times itself equal. So we could say, well, what times itself equal 4? 2. Or what times itself equal 9? 3. Or what times itself equal 16? 4. Sometimes when we have a radical, that's a square root situation, that radical simplifies into a whole number, and so the radical's gone. But sometimes the radical doesn't disappear, and so we need to know how to simplify those, just like we would learn how to simplify fractions like a third or a fourth or a fifth. Now, let me tell you why we need radicals again. I taught this on page 24 of the Algebra 1 text, but I'm just going to use the graphing calculator to show you something right quick. If I had something like 1/4, 1/4 is actually a terminating decimal. That's 0.25, which is 25 hundredths. If I took that 25 hundredths and I reduced it to a fraction in simplest form, it would reduce back down to a fourth. So terminating decimals have fractional equivalences. But what about a decimal like 0.333333333333333, a repeating decimal? For the calculator to recognize it repeats, we need to go over a line. And so we're going to say we'll turn that into a fraction, and it says a third. Well, how did it know that? Let's double check. 1 divided by 3, 0.3 repeating. And so we learned on page 24 of the algebra text that decimals that either repeat themselves or terminate can be turned into fractions. And we call those rational numbers. A rational number is something that can be written of the form a over b, where b is not equal to 0 because division by 0 is impossible. In other words, a rational number is something you can make a fraction out of. But what about, let's just take something that has two repeating digits like point 3, 4, 3, 4, 3, 4, 3, 4, 3, 4, 3, 4, 3, 4. Isn't this fun? 3, 4, 3, 4, 3, 4. What that turns into, if you change it to a fraction, if there's two repeats, you put the two repeats over 99, 34 99s. Well, if we had something like the square root of 2, square root 2, we get a decimal value that never repeats itself, nor does it terminate. To show you that that number 2 right there is not the end, I could subtract the 1 off, and you could see that after that 2 there was a 4, and we could manipulate it and see that there's more and more numbers. If it never repeats and never terminates, you can't write it as a fraction. Now, why did we even need to learn how to add, subtract, multiply, and divide fractions? Because fractions, some fractions like 1/3 and 1/6, represent repeating decimal values which you cannot write as a decimal. So the only way to effectively write that without rounding is to write it as a fraction. So since some decimals have to be written as fractions, then we have to learn how to add, subtract, multiply, and divide fractions, do all of the operations with fractions, and simplify fractions. Well, since not every decimal value that you cannot write as a decimal without rounding can be written as a fraction, like the decimal value for square root 2, that means that some decimal values have to be written as radicals, which means we need to learn how to add, subtract, multiply, and divide radicals, and we have to learn how to simplify radicals. So there's the need for simplifying radicals. Now you may recall in the Algebra 1 text on page 248, we said to simplify a radical, you ask yourself these 4 questions in this order after every single step. Question 1, see if anything reduce. Question 2, see if a radical will break down. Question 3, see if there's a fraction under the square root sign. And question 4, see if there's a radical in the denominator. If you get a yes to any of those, you've got to fix it. After you fix it, you have to go back and ask yourself those 4 questions in that order again, and you do that after every single step. You know you're through simplifying when the answers are nope, 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 nope. When you get 4 no's, you know it must be in simplest form unless you made a mistake. Okay, so question 1, see if anything will reduce. Now, we learned, recall, how to add, subtract, multiply, and divide radicals. We do it as if they were variables, which is the first thing I taught you in Algebra 1. Example, we said 2x plus 3x is like saying 2 bananas plus 3 bananas. When you add or subtract, the name stays the same. 2 of those plus 3 of those is 5 of those little x's. We said you cannot add 2x plus 3y because they are not like terms, and so we would have to write it back as 2x plus 3y, or say the expression is already in simplest form. Likewise, and we also learned this in Algebra 1, the name of the first term here is square root 3, so 2 of those plus 3 of those makes 5 of those little square root 3's. Just like you can't add x's to y's, you can't add square root 3's to square root 5's, so we would rewrite it or say that it's in simplest form. You cannot combine those. They are not like terms. That's page 1 of the algebra text. We said to add or subtract, the names have to be the same. In algebra, we call them like terms. When you add or subtract, the name stays the same. Page 5 of the algebra text, we talked about multiplication. We said when you multiply the numbers, and you multiply the names, and you get a new name. So we get 6xy. Likewise, we do the same thing with radicals. We would multiply the numbers 6, multiply the names, and get a new name square root 15. So hopefully you still recall that information from Algebra 1. Remember also that we can reduce radicals just like we reduce numbers by dividing each member by their greatest common factor. Now square root 3 goes into both of those. Square root 15 divides square root 3 is square root 5, and square root 12 divides square root 3 is square root 4. So that reduces to square root 5 over square root 4, but the square root of 4 is 2. What times itself is 4, 2. So this simplifies into square root 5 over 2. Any questions on example 1 through 4, the basics of adding, subtracting, multiplying, and dividing radicals? So when we say will anything reduce, we're thinking about those things. That was question 1, will anything reduce? Question 2, will a radical break down? Now, remember to break down a radical, we're going to do the prime factorization. We're going to circle pairs for square root. Had it been cube root, we would have circled sets of 3, fourth root sets of 4. So we're going to do the prime factorization of the number. We're going to circle pairs for square root. We would have circled sets of 3 for cube root. We're going to put them under the new square root sign. Then we're going to make a new square root sign. We're going to put 1 from each pair we circled outside. Put what didn't get circled in a set on the inside, and then you multiply the outsides, multiply the insides, and you're done. This little drill is on this page of the geometry book. It's on page 15 and 16 of the Algebra 1 book, and it's also on page 248 of the Algebra 1 book. So let's look at an example. Remember that prime numbers are numbers divisible only by themselves in 1, 2, 3, 5, 7, 11, 13, 19, 23, etc. So what we would do is we would take the radical part of that, the radicand, as we call it, the radicand, 3,780, and we would break it down. I'm going to move it over here just so I have a little bit more room. 3,780, and we're going to do the prime factorization. The smallest prime that'll divide into it is 2, and we're going to get 15, 1890 divided by 2 is 945. Divided by 3 is 315. Divided by 3 is 105. Divided by 3 is 35. Divided by 5 is 7. And so we did the prime factorization. What I normally do once I've done the prime factorization is I rewrite it as the product of those primes. This is what I did in Algebra 1. I would just put all those primes back underneath there just for organizational purposes. And then notice there was already a 3 out there, and we've got to put that 3. I'm going to keep it in green. And then since it's square root, we circle sets of 2s. So we've got a set of 2 2s and a set of 2 3s. We would make a new radical from there. The 3 that was already out there stays out there. From each set, we bring out 1 from the set. Don't bring out both 2s, only bring out 1 of those 2s. From that set of 3s, you bring out a 3. Did not get circled in a set goes back in. The 3 wasn't in a set, it goes in. The 5 wasn't in a set, it goes back in. The 7 wasn't in a set, it goes back in. We multiply the numbers that ended up outside. 3 times 2 is 6 times 3 is 18. We multiply the numbers that ended up on the inside. 3 times 7 is 21 times 5 is 105. And so in simplest form, it is 18 square roots of 105. Any questions on this example? Okay. Question 1, will anything reduce? That's basic addition, subtraction, multiplication, and division. Reduce number with number and radical with radical. Question 2, will a radical break down? What does it mean, will a radical break down? It means, does it have any sets of primes? If it has some sets of primes and something pops out. If there were no pairs, everything would go back in and you'd be right back where you started. So we would say, well, it doesn't break down because there was no sets to pull something out from. Question 3 is there a fraction under the square root? And to get a fraction out from under the square root, to get a fraction out from under the square root, you just split it apart. So we would just split this into square root 3 over square root 5. Now you can't leave it like that because the fourth thing says, is there a radical in the denominator? And you can't have that. On this one, notice we could reduce it first. 3 goes into 15.5, 3 goes into 18.6. We could split it into square root 5, 6, and then split it into square root 5, square root 6. Because remember, question 1 is rule anything reduce. Question 3 is there a fraction in there? So we fix question 1, will it reduce, before we fix question 3, which is split it apart, you see. Now, once you split it apart, you're not through. We're not supposed to leave that radical down there. And so the last thing is, how do you get rid of that radical? How do you not let there be a radical on the bottom? Well, we call it rationalizing the denominator. Now, in the geometry book, all we're going to do is deal with square roots here. And so we just simply need to know to multiply it by itself. But it's really more complicated than that. It's more complicated than that. What we said is, to get a radical off the bottom, we're going to multiply the top and bottom by that radical. That's on a square root. We call it rationalizing the denominator. A square root is an irrational number. We don't want it to be an irrational number. We'd rather it be a rational number like 5. Okay? Now, on page 15 and 16, 15 of the Algebra 1 text and 248 of the geometry text, of the algebra text, excuse me, it says to rationalize the denominator, you multiply by the square root of whatever primes it takes, so that each prime involved appears the index number of times. Now we're talking about square root. If there's not going to be a radical anymore, then underneath that radical there needs to be a pair of primes. Because if you have a set, you bring one from the set outside, and what did not get circled in a set goes back in. If everything is in a set, there's nothing to put back in, and so the denominator would become a whole number rather than a radical. So we're thinking, I need to multiply such that that prime appears twice. Well, for it to appear twice, I need it to happen one more time. That creates for me this situation, which is a pair of 5s, and so out pops a 5, and so my new denominator is 5. But what you do to the denominator of a fraction to manipulate it, you must also do to the numerator. Make equivalent fractions. It's like multiplying by 1 that over itself. So on the top we get square root 15, and so we get square root 15 over 5. Now we would have to go back to question 1, will anything reduce? Well, it won't, because you cannot reduce a square root with a number. Question 2, would the radical square root 15 break down? It wouldn't, because it came from a single 3 and a single 5. Is there a fraction inside the square root? No. Is there a radical in the denominator? No. So that must be the answer. Okay? So, to simplify a radical, you ask yourself these 4 questions in this order after every single step. Question 1, will anything reduce? Question 2, will a radical break down? Question 3, is there a fraction in the radical? Question 4, is there a radical in the denominator? If anything's messed up, you fix it. When you fix it, you ask yourself those questions again. When you get nope, 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 when you get a no to all 4 questions, then you know that the radical must be simplified. Okay? All right. So let's look at the daily work. This is a practice sheet for geometry radical review. Now, I have to test and retest this several times sometimes, and it's because it just takes a little bit of practice and digging and thinking and studying to get this down. So we're going to go through this together. Square root 25 means what times itself equal 25, so what times itself equal 25? 5. And then that brings us to number 2. And what we would do is we'd say, okay, the square root of 24, it doesn't have a perfect what times itself equals, so we're going to have to simplify it by doing the prime factorization. So we would rewrite that square root of 24 as the product of its primes, 2 times 2 times 2 times 3. Since it's square root, we would circle sets of 2. We would make a new radical. From each set, you bring 1 out from the set, only one of the 2's from the set. The numbers that did not get circled in a set go back in, so there's a 2 that goes back in and a 3 that goes back in. All numbers that went back in get multiplied together. All numbers that went out get multiplied together, so it simplifies to 2 square root 6. And that's the prime factorization method of breaking down a radical. I need to teach you the official geometry book definition method of breaking down a radical, okay? This is my method of breaking down a radical. But the official, like this isn't an official geometry book, but anyway, in an old geometry book I studied out of, it would say this: to be in simplest form, no factor of the radicand may be a perfect square other than 1. And so you'd think of all the factors of 24, not prime factors, factors. 1 times what is 24? 24. 2 times 12 is 24. 3 times 8 is 24. 4 times 6 is 24. So that's all the factor pairs of 24. What are the perfect square factors? 1 and 4. We want the largest perfect square factor. The largest perfect square factor of 24 is 4, so we could think of the 20 square root 4 times 6, because 4 times 6 is 24. And just like we busted the division of radicals, we can bust the multiplication of radicals. The square root of 4 is 2, and so you would get 2 square root 6. Remember when we did the prime factorization, we had 2 times 2 is 4 times 2 is 8 times 3 is 24. We circled the sets of 2. Do you see that that set of 2 is really the 4, which pops out of 2? And the leftover 2 and leftover 3 go back to make that 6. So if we do the prime factorization method, the pair is really that largest perfect square factor, and the non-circleds is that other factor. So if in your mind you can identify the largest perfect square factor and say, oh, 24 is 4 times 6, and the square root of 4 is 2, then you can get the answer without going through all that prime factorization and circle and sets thing. Okay? It's just a shortcut is all it is. All right. Let's look at number 3. We have 6 square roots of 540. We're going to take the 540, the radicand, and we're going to do the prime factorization. 2 will go 270 times. 2 will go 135 times. 3 will go 45 times. 3 will go 15 times. And 3 will go 5 times. Now we already had that 6 out there. So we're going to have 6 square roots of 2 times 2 times 3 times 3 times 3 times 5. We're going to circle sets of 2 because it's square roots. We have a set of 2 2s and a set of 2 3s. And then we're going to make a new radical. That 6 was already out there, so it stays out there. From that set of 2's, we bring out 1 2 from the set. From the set of 3's, we bring out 1 3 from the set. What did not get circled in a set goes back in. We multiply those things that ended up outside together. We multiply those things that ended up inside together. And so we've simplified that into 36 square root 15. Any questions on number 3? Now, I just did a whole lot of your work for you. If you don't practice this, you won't be good at it, and I guarantee you, you will fail the test. So I encourage you to do these again, even though you just saw them all worked out. Okay? All right. Now we're going to skip around just a little bit. Let's do number 5. We're going to go through the questions, remember. Now we've got some of this fraction-looking stuff. When they start looking like a fraction, then you got to say, question 1, will anything reduce? Question 2, will a radical break down? Question 3, is there a fraction inside the square root? Question 4, is there a square root in the denominator? And you ask yourself those 4 questions in that order after every single step. Number 5, question 1, will anything reduce? Yes, it will. 12/15 will reduce by dividing by 3 to 4 over 5. 12 divided by 3 is 4, and 15 divided by 3 is 5, so the fraction inside the radical reduces. Now, back to question 1. Will anything reduce? No. Question 2, will the radical break down? Meaning, if you did the prime factorization, would there be any sets of primes? No. Question 3, is there a fraction inside there? Yes, there is. If we're going to fix that, well, how do you fix that? Well, you just split it apart into a division sentence. Square root 4 divides square root 5. So we fixed that problem. But we got to go back to question 1 now. Question 1, will anything reduce? No. Question 2, will a radical break down? Square root 4 will. What times itself equal 4? 2. So we have 2 over square root 5. Well, back to question 1. Will anything reduce? No. Will a radical break down? Will square root 5 break down? No. Question 3, is there a fraction inside there? No, there's a whole number 5. Question 3, is there a square root in the denominator? Yes. So we're going to multiply by the square root of whatever it takes, and so that that 5 appears twice. So that there's a set of 5s, and out will pop a 5 and make our denominator 5. Well, to have a pair of 5s, we just need one more of them, which would create that pair and pop out a 5. So we're going to multiply by square root 5, and square root 5 times square root 5 looks like that, which is really square root 25. And what times itself is 25 is 5. Either way you want to look at it. You got a pair of 5s, so out pops a 5. it turns into square root 25, which is 5, so out pops a 5. Whatever you did to the denominator, you must also do to the numerator to make equivalent fractions. And so you're going to have 2 square root 5 over 5. Well, back to question 1. Will anything reduce? Well, you can't try to do the square root 5 and the 5, just the 2 and the 5. Will anything reduce? Nope. Will the radical square root 5 break down? Nope. Is there a fraction inside there? Nope. Is there a radical in the denominator? Nope. We got nope, 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 nope to our questions. Therefore, it must be simplified. So the simplified version is 2 square root 5 over 5. Okay, any questions on that? Now, some of what we're doing here may be just a little more complex than we need for geometry, but that doesn't mean you don't need to learn it. You need this stuff for Algebra 2 and for college algebra and pre-calculus and calculus. So everything we do is a foundation to something else you're going to do later. Okay? Let's look at number 8. Number 8. Question 1. Will anything reduce? Yes. 6 will go into 18.3, so we're going to have square root 10 over 3 square root 3. Back to question 1. Will anything reduce? Nope. Look, will a radical break down? Well, you may think, well, that 10 does. Well, let's check it out. That's not very good. We'll come to the other side. Over here, 10 divided by 2 is 5. To break down, there would have to be a set of 2 to pop out. Well, there's not a set of 2 of anything, so nothing will pop out, so the radical will not break down. Question 3, is there a fraction inside either radical? No, inside the top one is the whole number 10, inside the bottom one is the whole number 3. So question 1, will anything reduce? Nope. Question 2, will the radical break down? Nope. Question 3, is there a fraction in the radical? Nope. Question 4, is there a radical in the denominator? Yes. So we're going to multiply by the square root of 3. That creates a pair of 3's that would be in a radical like this. And so it would pop out a 3 from that radical. But this particular one already had another 3 out there. So it's out there with the 3 that we popped out from the set. What you do to the denominator, you must also do to the numerator to make equivalent fractions. And so on the top, we get square root 30. The 3 times the 3 is 9, so what we have is square root 30 over 9. We go back to question 1. Will anything reduce? Well, you can't reduce a square root with a number, so you can't even try to reduce the 30 and the 9. Question 2, will the radical break down? Well, somebody might think, well, that 30 will break down. Well, let's check it out. What are we looking for? Pairs of primes. 30 divided 2 is 15 divided by 3 is 5. Pair of 2's, nope, it's a single. Pair of 3's, nope, it's single. Pair of 5's, nope, it's single. There were no pairs of primes, so the square root of 30 will not break down. Question 3, is there a fraction inside the square root? Nope. Question 4, is there a radical in the denominator? Nope. So that radical has been simplified. Any questions on number 8? Okay. Now some basic adding, subtracting, basic operations with radicals. Remember in the Algebra 1 text we said, okay, what's the operation? The operation is addition. What's the rule for that? To add or subtract, the names have to be the same. In algebra, we call them like terms. When you add or subtract, the name stays the same. So 6 of those plus 8 of those makes 14 of those little square root 2's. That's how we did it. Okay? When you multiply, this is page 5 of the algebra book. We did this little jingle. You multiply the numbers and you multiply the names and you get a new name. Will the square root 6 break down? No. Need to check that. Let's look at number 16. We can cross-reduce when we're multiplying fractions. Square root 3 goes into square root 6, square root 2. That square root 2 will cancel with that square root 2. 4 goes into 8 twice. 3 goes into 9 3. We multiply what's left. What's left is a 2 on square root 2 on top and a 2 on top and a 3 on bottom. So we're left with a 2 square root 2 on top and a 3 on bottom. 2 square root 2 over 3. That 6 is actually gone there. It's not slashed real good. 2 square root 2 over 3. Will anything reduce? Nope. Radical breakdown? Nope. Fraction inside the radical? Nope. Radical in the denominator? Nope. So that's it. Okay? This is a little reminder of exponential law. Exponential law, this exponential law is on page 13 of the Algebra 1 text. And this is 3 to the negative 1. And remember that the negative is a command to what? Remember that? It's in an oval in the middle of page 13 in the Algebra 1 text. We read the negative as the reciprocal of. Now, you need to know that when you move into Algebra 2, college algebra. We read that as the reciprocal of 3 to the first. Now, the reciprocal means flip it over. 3 to the first is 3 over 1. Its reciprocal is 1/3. So 3 to the negative 1 says the reciprocal of 3, and the reciprocal of 3 is 1/3. Also on page 13 of the Algebra 1 text, we learned that any number raised to the 0 power is 1. And we proved why on page 13 of the Algebra text, and you can go there for that proof. We learned on page 13 of the Algebra 1 text that any number raised to the first power gives you that number. The second power is times itself, which is 9. And again, I encourage you to go to the Algebra 1 text. If you don't have one in your hands, you can go to www.dballardproductions.com. And you can find the algebra text there, and you can look these things up. Okay? We have some more practice with those. Now, also, in the Algebra 1 text on page 13, we talked about the half power. We said half power means square root. And so we have the square root of 8, which we would have to break down to see if that's in simplest form. We would rewrite it as the product of its primes. We would circle sets of 2 for square root. We would make a new radical. For each set, we would bring 1 from the set out. What did not get circled in a set, we would put back in, and so we would have 2 square root 2. Okay? The third power, you can find that. It means cube root of 8, and I'll let you finish that. 8 to the 2/3. You may recall on page 171 of the, let me see, 168, 169, 170, 170, excuse me, I had to flip pages in my mind, of the Algebra 1 text. We said when you raise a power to a power, you multiply. So we can see this as 8 to the 1/3 squared. because when you raise the third to the second, you would multiply 2 times a third is 2/3. The third power is cube root, so what we have is cube root of 8 quantity squared. Cube root means what times itself 3 times equal, and what times itself 3 times is 8 is a 2. So we end up with that 2 squared, which takes us to a 4. Okay? So we're using some exponential law to bust that 2/3 power into the third power square. Recognize the third power is cube root. So we got the cube root of 8 squared. What times itself 3 times is 8? 2. So 2 squared is 4. Okay? At the end of this, we have scientific to standard notation. Scientific notation is written with a base of 10. Times 10 to the fourth means that you'd multiply by 10 4 times, which would move your decimal 4 places to the right. So you would have 3, 6, 2. You'd have 2 more places that you'd put zeros in, and you'd have 36,200. Okay? The negative on the exponent is a command to reciprocate. So that's like times 10 times whenever the negative reciprocates it, 10 to the third, or times 1,000th. So it's actually going to get smaller by multiples of 10. 3 moves. Puts our decimal here, fill in the zeros, 0.004684. Okay? Remember that the negative is a command to reciprocate. So we're really dividing by tens instead of multiplying by tens when the exponent is negative. If it's already in scientific, if it's already in standard and you want to go to scientific, we would make that 8.42, and then we'd say times 10 to the whatever it takes to make it little again. To make it little again, we would have to divide, which means we need a negative exponent, and it would take 2 moves to put it back, so we need to the -2. The -2 would say times 10, it would say times 1 over 10 squared, which is like dividing by 10, and dividing by 10, which is divided by 100, okay? All right, to put this in scientific notation, again, we're going to shift our decimal so that our decimal is after the first whole number. So we're going to move it 1, 2, 3 places. So we know this is going to be 4.68321, which could be rounded to 4.68, times 10 to the something. Now, what we've done is we've made this number way too little. So we're trying to make it big again. To make it big, we need to be multiplying by 10s, so we need a positive exponent. We had shifted it 3 times, so that exponent's going to be a 3. Any questions on that? At the bottom, it says use the diagram to reach conclusions. We have to study that just a little bit. It's a little bit complex, but it leads into the next lesson. If we were to solve this proportion, you would have AB times AB is AB squared is equal to AD times AC, AD times AC, or AC times AD, either way. And then you'd get rid of the square with the square root. So you have AB as the square root of AC times AD. AC is the hypotenuse. AD is the closest piece to AB. So the one leg AB comes out to be equal to the square root of the hypotenuse times the piece of the hypotenuse closest to that. Okay? BC times BC is BC squared. That's equal to AC, which is the hypotenuse, times DC. This piece BC came out to be equal to the whole thing AC times this little piece DC based on the similar triangles. You studied all of that. And so we have BC, if you take the square root, is equal to the square root of AC times DC, which is the hypotenuse times the closest piece again. And you can continue that. Okay, that's kind of got you going there. All right, that's the pre-chapter 8 skills and practice, and then that's going to lead you into the rules on page 195.